Want to make a prediction for a branch B1 or B2, you will go to the local predictor. The local predictor will tell you some prediction. Yeah. So P L, and you will also go to the global predictor. The global predictor will tell you some other prediction or the same prediction. Let's call it PG. And then you must have some mechanism by which you should be able to select between the two, that is PL and PG, and this is your final prediction, right? So this mechanism here is what we were calling as the selector. So you should have some you should have some local predictor. It could be a single bit predictor or a 2-bit predictor, any configuration. You should have a be a correlating predictor or any other configuration. I will show you one more configuration today. And then you should have a selector. The selector should be able to select the correct predictor from amongst the local and the global. So there are three components in this: two, and the selector is the third component. So with the reference to the Alpha 21264 processor, we will see what is the configuration of 1, 2, and 3. How do they look like in hardware? With the selector, last time also we had started off with the selector. So start off with the selector. So what I was telling, okay, you have a branch B1, you have a branch B2, and so on. Selector is nothing but in the Alpha 21264 processor, select storage space or a buffer. Okay, so this is a selector. Total size of the selector is 4K entries. So there are entries in this buffer. Selector is nothing but a buffer. Okay. Total 4K entries. All right. And each entry of the selector is 2-bit. So suppose that you have reached, you are executing your piece of code and you have reached branch B1, and for B1 you want to now make a prediction. So both the local predictor and global predictor would be making some prediction for B1. Now you need to do a selection out of the two. Which one do you choose? So for doing selection, what you need to do is 4K entries. So take 12 bits of address, and with the X into the selector. Here you will read 2 bits, 00 or 01 or 10 or 11, right? That are the four possibilities that you will have. Now, of the four possibilities, two combinations would be saying that use the local predictor. Would be saying that use the global predictor. So if you read a, use the prediction from the local predictor. If you read a 10 or a 11, you will use the prediction from predictor. All right. Now you can dynamically move from using local predictor to a global predictor depending upon which of them is showing you the correct behavior, right? So over time you can move from one to another. So there has to be a logic behind that, and the logic behind moving from local predictor to global predictor or vice versa is captured here in this state diagram. So there can be different logics that you can use. I am showing you one with the help of this state diagram. That is, how do you actually decide which one of the two to use? And later on, you can also change you are using local predictor, but you can go and start using global predictor at a later point of time. Okay. So this is the state diagram which is used by the selector. And let us say, you can see here there are four states. Four states correspond to the four combinations that you have: 00, 01, 10, and 11. So let's say this is 00, this is 01 corresponding to 01. All right. This is, let us say, 10, and this is 11. Okay. Use one, use two is nothing but use, I mean, let us say one is your local predictor. So use local predictor. Here also it is like use local predictor. Two is corresponding to the global predictor. So there are two predictors, one and two, or local and global. All right. Now, suppose that in the beginning, for the first time, you came to B1, you indexed into the buffer, and from the selector buffer, you read a combination, and let us say that combination turned out to be 00. All right. Now, if that combination turned out to be 00, what is the prediction that you are going to use for B1? The prediction is that use the local predictor. Is that your prediction could be wrong or your prediction could be right. Based upon that, you will keep on using either the local predictor or you can move to using the global predictor. So what is the logic which is captured here in this state diagram? So let us check. So you read a 00 and you said that, okay, please use local predictor. But now you go and check in the ID state, the branch will be actually resolved and you would know whether it is actually taken or not taken. And hence you will know whether your prediction was correct or not. Right? So let us say that for B1, I wanted to make a prediction. Local predictor is saying something, global predictor is saying something. Now, what I local predictor, what could happen is that I go wrong. So I use the local predictor and I have gone wrong. At the same time, I also know what the global predictor was saying, but I would have again gone wrong. So the two zeros here are telling me what were the two predictors I would have used them. So if you go wrong, right, you were using local, but you have gone wrong. But had you used global, you would have still gone wrong. You do not really know what is the change that you should do. I mean, whether to keep on using local predictor or to switch to global, you really do not know, right? Because both have, you remain in the same state. What is the other possibility? The other possibility, local predictor which you used is correct. It gave you a correct prediction. But the global predictor, had you used that, it would have given you a wrong prediction. Then in that case, definitely I want to remain in this state. Right? The third possibility is that local predictor is correct. Had you used global, that would also have been correct. Then in that case also you remain in the same state. Right? The last possibility is that you use the local predictor, but it is wrong. So your prediction has gone wrong. And at the same time, you see that had you used the global prediction, your prediction would have been correct. In that case, we move to the second state here and we will change 00 written here. I will change it. So a 00 was written here. It still says that when I will encounter B1, I will still be using the local predictor, but my confidence level is now down. So if you have changed this to 01, you have changed these bits to these bits here to 01, and you again come to B1, later on at some later point of time. Now you will read a 01, you will still be saying that please use the local predictor. Okay, so your prediction, whatever the local predictor is saying, that you would be using. Now, again, you could be wrong as well as the global predictor could be wrong. So you will remain wherever you are. Or both the predictors are right. So you will remain wherever you are. Correct? Or the other possibility is that the local predictor which you used is correct and the global was wrong. So in that case, your confidence will be restored and you will move back to this state. And the last possibility is that the local predictor is again wrong, but had you used the global predictor, you would have been right. So in that case, now go to this state and in this state, you can see here that you will start using the global predictor. So that is the selector logic, which is captured in this state diagram. So using this logic, you will go on changing the bits of the selector, and the selector is nothing but a 4K storage, and each entry is a 2-bit entry. And this is stage number 3. That is this one. So selector, what it looks like. This is what the selector looks like. Clear? Or any doubts or any questions you have? Okay. So selection logic, I believe, should be clear to now. What else is remaining? We need to see what the global predictor looks like and what the local predictor looks like. Now, this is something that you can choose. You can use any global predictor or any local predictor. One global predictor that we have seen is the correlating predictor, which we discussed in the last class. So you can have a correlating predictor here, right? But in alpha 21264, you have a slightly different configuration. So I will just tell you about that. 21264. So as far as the global predictor for the global predictor configuration looks something like this. Okay. So it is a 2-stage process. So in the first stage, you have a sort of register, shift register, which has got 12 locations in it. So there are 12 entries. Okay. Now we use this shift register, 12-bit shift register, to capture of previous 12 branches. Now they can be anywhere. So you have a B1 here, you have a B2 here, you could have B3 here, and so on, right? Previous 12. That is what we capture in this register. That's the first part of the global predictor. So suppose that I have all ones here, right? So if I have all ones here, it is essentially saying that at any point of time, if I check, means that the previous 12 branches, which are anywhere in the code, were all taken. And then let us say, currently I execute a branch and that's not taken. So what I will do is I will do a shift left and I will put a 0 here. So I'll say that all the previous except for the most recent one, which was not taken. So I will have my pattern history of the previous 12 branches which have been taken or not taken. Any previous 12 in the code. That's stage number 1. Now for stage number 2, for the global predictor, what you have again a buffer. So this is a buffer which has got 4K entries. All right. So what you do is you check out what your branch history is, previous 12, right? So take that bit combination and index into the second stage. 12 entries in the first stage, so 2 to the power 12 is 4k. So that is why you have got 4k entries in the second stage. All right. So see this here. This is the first stage, and this is the second stage. This is your global predictor, which I was drawing for you. Right now, each entry here is a 2-bit entry. Each entry here is a 2-bit entry. Now, depending upon, so 2-bit entry means 4 possible combinations, 0, 0 to 1, 1. All right. So two of these combinations will tell you that the branch is not taken, and two combinations will tell you that the branch is taken. Okay. So you want to just make a prediction for B1, let's say. Right? How would you make a prediction for B1? What is the global predictor going to do? So whenever you want to make a prediction for a particular branch, you just go and check what is the bit combination here, right? Using this bit combination, index into the second stage, and in the second stage you will read a 2-bit value, and from this 2-bit value you will get what is the prediction, whether not taken or taken. Finally, B1 would be either taken or not taken. So your prediction could be correct or it could be incorrect. So whatever be the outcome of B1, that you insert here, right? And then change this combination, I mean, whatever is written here, depending upon a particular state diagram. That state diagram could be simple 2-bit predictor that we had discussed earlier, a simple 2-bit predictor state diagram that we had uh, discussed earlier. So Alpha 21264 uses this kind of global predictor. There are many schemes that are used for global prediction, and same way for local prediction also. So this is one of the schemes which 2126 is the global predictor. So what you will have is this. So this hardware is in selector, right? And this here is going to be in the global predictor, right? So that leaves us with this component, which is the local predictor. Local predictor could be a simple 1-bit predictor or 2-bit predictor that we have earlier discussed, but I will tell you what 2126 will tell you that. So the local predictor of 21264 again is a 2-level, 2-stage predictor. Okay. So you have here branches B1, B2, and so on. In the first stage of the local predictor, you can see here that you have this buffer or a storage space where you have 10k entries. So total number of entries, sorry, 1k entries. Total number of entries are 1k. That's 10246. So you can imagine in the first stage, there are sort of 1024 registers. Okay. Now each register, each of these 1024 register is a 10-bit register. Each register. Now suppose that you are executing your piece of code and you come to B1, and using the local predictor you want to make a prediction for B1. So what are the steps that you will take? First thing is, to index into the first stage you would need some bits from the address. How many bits would you need? for the first stage?
10 bits.
10 bits, correct. Because total number of entries in the first stage are 1024. So take 10 bits and index. Now, here you will read a register, and what do you read in a register? The total number of bits that you read in a register are 10, right? So the output that you will get here, is a 10-bit value. And of course, the address is also 10-bit address to the register, right? Okay. Now, in every register that you read, what is it that is stored? Now, every register that you read track of the previous 10 outcomes of the same branch. Happen to B1 previous 10 times, that is stored in the register corresponding to B1. Whenever you index using the address of B1, so suppose this is the register corresponding to B1 where you index corresponding to B1. So this is where you are going. So what you have here is nothing but the history of the previous 10 outcomes of B1. So see that this is a local predictor. I want B1 based upon its own behavior. I don't want the outcomes of B2 or B3 to be taken into consideration because I know B1 is a local branch. Its behavior is only dependent upon its own outcomes, right? For the previous 10 outcomes of the same branch. So for example, just like you have a B1 for if you were to make a prediction for B2, you will take the lower 10 and again you would have indexed register corresponding to B2, you would record the previous 10 outcomes of B2. So you can imagine that these individual registers are of the shift kind. So every time you have a new outcome of a branch, you can feed it in, you can shift value. The oldest value will be dropped and the newest value will come in. So you record the previous in these shift registers, right? Okay. Now, depending upon the previous 10 outcomes of the branch, which you will be reading here, you go to the next stage. And the next stage of the local prediction going to have, you can see here, there are 1K entries. So total number of entries that you have here are 1K, so 1024. That's why you have 10 bits. Using these 10 bits, you can index into any one of the 1024 entries, 1K entries you have, right? Each of these entries is a 3-bit entry. Each of the entry here is a 3-bit entry, right? So you wanted to make a prediction for B1, you index into the first stage. From the first stage, you read the 10-bit combination, right? After reading the 10-bit combination, go to the second stage. Uh, Read the corresponding 3 bits. So what would you read? You would read a value 7. All right. Now, the second stage works like the counter. I had discussed this also earlier with you. So, what you do in the second stage, if you read anything between 0 to 3, you that the branch is not taken. And if you read anything between 4 to 7, you say that. Okay. And every time the branch is taken, you increment the counter and it will saturate at 7. And every time the branch is not taken, you decrement the counter, it will saturate at 0. So second stage, but it consists of 1024 saturating counters, 3-bit counters. right? So this is what the local predictor for 21264 looks like. As I have said, there are many combinations which have been studied for global predictor as well as for the local predictor. I have just told you one or two of them, right? So this is the basic idea behind the tournament predictor. And as I have said earlier, all the present day processors would have a prediction logic which will be on the processor die, and it would be of the tournament kind. So there will be a local predictor, there will be a global predictor, there will be a selection logic. All the present day processors would have a predictor of this kind, right? So, any questions or any doubts you have?
Sir, in this local predictor, if
Yes,
a branch is taken or not taken, as in once we get to know whether when after it was resolved, when we get to know if it was taken or not taken.
right.
So of these, the first stage and the second stage, are the bits in both these stages updated?
Yes, yes, yes. So
Okay.
depending, see, every time you encounter a branch will be taken or not taken. So that you have to update here, one thing,
Yes, sir.
right? And second thing is that every time a branch is taken or not taken, so you may have to increment the corresponding counter or decrement the corresponding counter.
Sir, so now this 10, once we alter the first stage, so this 10 bits will change. So how will we remember which part to alter in the second stage?
No, the point that we are saying is that we are saying if the previous 10 outcomes of B1 were such and such, then in that case, what is the prediction that we would want to make? If the previous 10 outcomes of B1 are something else, then what is the prediction that I would want to make? So you can imagine that depending upon the previous 10 outcomes, you are using either this predictor to make the prediction, or some predictor here to make the prediction, or some other predictor. So any one of them you could be using, which would be dependent upon what is the bit combination that you want to make, right? So for example, let us say that first time you encounter B1 and I want to make a prediction for B1, and let us say that everything here is a 1. So everything I read here is a 1, let us say. Okay. So what you would do, you will go to this last counter here and you will read what is written here. So let us say here also everything was a 1. So I read a 7, and I will say that the branch is taken. So my prediction is that it is taken. Now I will also come to know what happened actually to the branch, whether it was taken or not taken. So one thing, suppose that it is not taken. I am saying taken, but the branch is not taken. So if it is not taken, one thing that I will do is I will make this a 0. Pattern that will change. Okay. And what I will do here in this particular case, I would say that this will be decremented. So instead of 7, it will now become 6. So next time you index ones and you index here, you are not that confident about saying, you will still be saying that the branch is taken, but your confidence level is going down, right? So uh, this
Sir,
yes, yes,
so my confusion was that once it was not taken in the first stage, we inserted that 0 from the right.
yeah,
Now, this is pointing to the second last entry in the
yes,
second stage.
correct. So it is
So
quite,
how do we change the last entry only?
it is
How do we remember that we have to change the entry to 1110? Because now it is pointing to the second last entry.
right, right. No, so see the visualization is that if the previous were all ones, previous 10 outcomes of a branch were all ones, I will be using one counter to make the prediction. If the previous 10 outcomes were all zeros, I'm not using the same counter to make the prediction for the branch. See, I could use any of the 1024 counters, but which one I use, that is going to be dependent upon what are the previous 10 outcomes. So next time I will not be using the last one. So I will be using actually this one, because I'm saying that all the complete history of what happens if the previous outcomes were all ones and zeros is recorded in this particular counter. All zeros, this is capturing the behavior. So if the previous were all zeros, what happens to the next? That behavior is being captured by one counter. If it was all ones, what happens next? That behavior is captured by another counter.
Yes, sir.
That is the way it is going, right? Did I make it clear?
Yes, sir. Understood.
Right, right. Now there are issues with this kind of implementation. So any issue coming to your mind? I will tell you one. See, the issue is, one issue, of course, is which can be easily resolved is something like this. Suppose that I wanted to make a prediction for a branch having here a one, all right? And hence I went here and made prediction B1. And then I also did a modification here depending upon the outcome of B1, right? Now it is possible that B2 is indexing into this location, and B2 also I see that everything was a one. So then what I will do, I will again go here, right? And B1 is modifying this counter, B2 is also modifying the same counter, and you can see that this is a scenario which is similar to aliasing, right? And you will have an interference for prediction of B1. So you may not get good results in this particular case. Did you get the problem and see the problem? So if you have understood the problem, what could be a solution to this? Can you think of a solution? Right? So see, the problem, as I was telling, is that you could have two branches which have got exactly the same bit pattern, previous 10 bit pattern. And in that case, you would be, I mean, going to the same second stage entry, and you would be, two different branches are modifying that counter, which is used for the prediction. That's interference. So what could be one simple way of solving the problem? Any idea? Anybody?
Maintain separate such tables for every such branch.
Exactly. So second stage, instead of having only one set of 1K 3-bit counters, you can imagine that use for every branch a separate second stage. For B1 use, I mean for first branch, use one such structure. For the next branch, use another separate structure, similar kind. Next branch, again use a similar structure. So you are saying that you will be making a prediction for 1024 branches. So have 1024 different second stages. To overcome the aliasing. But the problem is, what is the problem there? What is the downside of that solution? If you have so many different 1024 different second stages, ultimately this has to be implemented 3-bit counters, right? So you have to implement all of them in hardware. So if you use separate second stages, the amount of hardware that you will end up using will be quite a lot. And whenever you are doing a predictor, you will be worried about how much hardware you need to fabricate, because the predictor is also going to be sitting on the same die as the actual processor. So you don't want the predictor to have a lot of hardware, because then you will have less space available for doing rest of the things. So there is a plus and minus of you will definitely accuracies, that's fine. But then you will end up using a lot of hardware. Use of extra hardware justify? I mean, is it justified? That would be dependent upon what is the gain in the prediction accuracy that you get. So 21264 uses just. So let us see what is the total amount of hardware that you end up using for this predictor, which is used in 21264. So you know selector is 4K entries, each entry is 2-bit, right? This is your selector. All right. And the global predictor is 4K buffer, each entry 2-bit. And this is your local predictor. So much of storage you require. Local predictor, first stage is 1K cross 10, second stage is 1K cross 3. This is 29K bits. And I told you that this predict, and you cannot afford a lot of time in making this prediction, because it has to be fast. It has to be made up of storage which is fast, and that storage which is fast is SRAM. SRAM, each bit requires 6 transistors. So in this project, approximately 180,000 transistors, right? So this is the kind of you will end up using. We want to keep this as less as possible while getting good prediction accuracies. So this is about the tournament predictor, and with this we are done with the prediction. Let's see what is the kind of accuracy that we get if we use the tournament predictor. So you can see one bar chart here where the light blue is, and purple is the 2-bit counter. And there is another predictor which is used here, which is actually a static predictor, profile based predictor, that we have not discussed in detail. See that the tournament predictor over different benchmark programs give you good accuracies, 94%, 96, 98. Now you can see that the values have started touching 98, 100, and so on. Right. This is another graph which tells you about how good the predictor is. So on this axis is the size in kilobits, and on this axis is misprediction. Misprediction. On these are average values which have been plotted over spec 89 benchmark suite. So you can see this green is the tournament predictor. and 2.5 average of 2.5% misprediction is what you get if you use a so that's good. Right. So I am done with discussing the predictors with you. Now, only one last thing, and this is about, see, all this while we have been saying that this is your IF stage, this is your ID stage, this is the EX stage. When the branch is in the IF stage, at that point itself, you want to make the prediction. Okay. So in the memory, there is a PC. PC is sending out an address. And using this address, you want to find out that the instruction is branch and you want to make a prediction for this particular branch. So your prediction logic is here that we were just talking about. Okay. So take PC and go to your prediction logic. And whatever be the prediction logic, doing a prediction. Whether or not to use that prediction will depend upon whether the instruction that you are fetching is branch or not. Okay, if the instruction is branch, then only you want to make use of this prediction here. If the instruction is not branch, you don't want to make use of this prediction. So you should know that the instruction that you are fetching is branch. For you to be able to do that, what we do is that we have a small storage present. You can imagine that is also present in the IF stage. So you can imagine a small storage present in the IF stage. So you take this PC value and go into this storage. Okay, this is the structure of the stuff. You can imagine two values. Every entry is two values. So you take the value of PC, right? So PC is here. So take the value that you are sending out by PC and go into this buffer. We call this buffer as branch target buffer, right? In this branch target buffer, I will keep on recording all the values of PC at which I find that the instruction which I fetched was a branch. Not know that the instruction is branch, but first time when I execute any branch in the ID stage, I would know that it is a branch and I make an entry for it. So I say that address A1, I found a branch, and what is the target for that branch I record here. Time I encounter the next branch, I will say, okay, at this address, I found another branch, and the target for this branch is such and such. So now, after you have recorded your entries in the branch target buffer, any time next when you encounter that branch, you will do a match. So all the entries you will match. Getting is this equal? Is this equal? Is this equal? Do a quick match. And if you find that a value of PC, what you have stored here, you immediately know that the instruction is branch. Right? And not only you know that the instruction is branch, you would also know what is the target. So in case the predictor is saying that the branch is taken from this memory itself, you can read the target. So target you store. And subsequently, on repeated use of the branches, you can pick out branch target buffer. Right? So take the value of PC, check out whether it is matching with any of the entries here, and then if there is a match, you know that the instruction is branch, and target also you can work out. Is there any issue with this implementation? So this is a storage space. You can imagine it is a storage. Is there anything coming to your mind, any problem, or is everything fine? So if this is a memory at different locations in this memory, and later on, whenever a value is given out by the PC, I want to find out is it matching with any one of A1, A2, A3, etc. Right? Suppose I want to do that. So if I do this sequentially one after this is going to be problematic, right? You cannot do this match sequentially one after the other. So the only issue is that this you should do in parallel. A1, A2, A3, match them with the value of PC in parallel. Do it. You will not have enough time. So to be able to do it in parallel, the way this particular memory is implemented is what we call as content addressable memory, or SCAM in short. Sometimes we also call it associative memory, right? So the only thing is that in this content addressable memory or associative memory, don't worry about the implementation. The only thing to keep in mind is that to this memory, I will give out addresses, a single address, and I can do this comparison in parallel. So when I send out a value, whether it is equal to this or this or this, any of them, this comparison I can do in parallel. This is the structure of the associative memory. Locations, many places. I do not know whether in operating systems you have a structure called TLB, translation look aside buffer. Have you discussed that or no?
Yes, sir, just yesterday we did.
Yes. So do now you will recall. TLB is also associative kind of memory. So there also you need speed of comparison. So that is the only thing to keep in mind. So this is the associative kind of memory that you will have. And using this, you can quickly find out that the instruction is branch or not. If it is branch, you can also know the target. Okay, so we are done with the branch prediction, but I have taken more time than required actually. So, but no problem. We will start discussing cache in the next cycle. Now, this is the only point when you will discuss cache. I don't think in any other course we will talk about cache. So it is very important. These are basics about cache. I will start from scratch. I do not know whether you did something in digital design. I was asking not much you did in digital design. Am I correct? Mapping, cache mapping, etc. Did you do last time or no in digital design? So no issue.
No,
Yeah, somebody was saying something.
no, sir, we
No,
haven't done.
no. Okay. So I will start from the basics. I will tell you about what is the cache organization, some idea about the cache, because cache is something using which we get a tremendous improvement upon the performance of the processor. Till now, we were only trying to do something to the processor architecture. Now we will see that the associated memory with which the processor is working, if we can do improvement upon that, we can get an overall improvement in the system performance. So that we will do in the next class. Then another thing is that your midsem papers are done, but I think you have a test tomorrow, right? You have a tutorial test of operating system tomorrow. So maybe we will then have a distribution on Friday. So I will tell you the time when we will have Friday class. We will meet first, then we will decide. Okay. Okay. So today we will stop here.